Okay, let's go ahead and get started. So thank you everybody for taking some time out of your day to learn a little bit about some of the great science coming off the Green Bank Observatory. I'm Karen O'Neill. I'm the director of Green Bank Observatory. So we're going to go through this. If you haven't been through these, I'll start off with just a few minutes of some news about what's going on around the site, what's going on with Green Bank Observatory. And then we'll move on to the highlight, which is a science presentation by Laura Woltz at Manchester University, talking about H1 constraints from the eBOSS galaxies and some GBT intensity mapping. So with that, let me just talk to you guys a little bit about what's been going on around the site. Of course, COVID is on our mind, as it is with everybody here. The number of positive cases of COVID around the state of West Virginia has been remaining steady, but at about 3% of all tests that are done are positive. Vaccine distribution is going better. I just noticed an error in my slides, is going better than my slides appear. So we've got about 32% of the entire West Virginia population is fully vaccinated, not 2%, with about 39% fully vaccinated. And within the county, we're doing a bit better than that, with 37% fully vaccinated and quite a few more partially vaccinated. That's the good news. The bad news is the distribution of the vaccine has been slowing down. So we had an initial fantastic run, but just like across the entire US, the number of folks getting their vaccine is now slowing down. Hopefully we'll be able to continue to get the vaccine out and into people's arms to really get a handle on this pandemic. The county itself has been doing fairly well in terms of infections. We've had a few infections around the county, a little bit through the school system. So the schools were closed for a couple of days last week, but otherwise things seem to be improving. And as I said, the number of vaccines continue to be distributed out there, including out into the school systems and so forth. So that's good news. On the site itself, of course, we remain in full operation 24 hours a day, 7 days a week. That's been great. Summer maintenance for the GBT begins next week. We have a slightly extended summer maintenance period this year to make up for some of the time lost last year due to the COVID-19 pandemic. So next year, our summer painters are showing up on site to begin their training. You can see one of our painters from a couple of years ago hanging off the GBT in the image up there. And so we'll be in 4 days of maintenance most weeks this summer, all the way through the end of September. We have a few exceptions out there, both for some of our observer training workshops, as well as to just make sure that we're able to still achieve all the science that the time allocation committee and our contracts want us to do. But nonetheless, we will be moving into summer maintenance from Monday morning through Thursday evening most weeks till the end of September. Also, as I mentioned 2 weeks ago, our outdoor tours, demos, and presentations have restarted, which is great. The weather is also fantastic right now. It's 70 degrees out Fahrenheit, and that's just wonderful. So if you're in the area or thinking of coming in the area, you can reserve your spots in advance and do a nice walking tour to come and see the observatory and listen to talks about the great science as well as the great engineering on site. Last week, we also had our conference, which was celebrating 20 years of science from the Green Bank telescope. It was a fantastic conference, great chance to hear stories about the telescope, learn about some of the great science with the telescope, and also get to connect with a lot of our GBT users over the last 20 years. If you missed it, the good news is it was all recorded. That's one of the wonders of Zoom. And so videos of the conference and each of the conference sessions, is posted online. You can just go to greenbankobservatory.org and you'll be able to readily find the link to the celebration. Just follow that and you'll be able to see the talks. The agenda is still there, so you can pick out which videos you want to see. Other than that, just a reminder of things that are coming up. Of course, we're continuing our biweekly Zoom meetings. In 2 weeks, we've got Helene Courtois of the University of Lyon talking about cosmic flows and some of the discoveries using the GBT as well as other telescopes around the world. And then 2 weeks after that, our own Natalie Butterfield will be talking about molecular gas in the galactic bar. We also have our observer training workshop coming up next month. That sign up is now closed. We are completely full, in fact, a bit over full. And all of the applicants are now being notified if they haven't received their notification already, whether or not they'll be able to be in that school. Again, those schools happen on a regular basis. The next one will be in September, and we encourage people to, if you wanted to attend this one, weren't able to sign up in time or weren't able to get in, please come back in early July when we'll be opening up signups both for the single dish school, which is a much longer training school, as well as the observer training workshop that's affiliated with that. So with that, I'm going to stop sharing my screen and hand this off to Laura Waltz to talk about some of the great science with the GBT. So thank you.
Great, thank you. Let me bring up my slides. I hope you can see them. If not, I'm sure someone will notify me.
Yes, they look good.
Excellent, thank you. Right, so thanks so much for having me, inviting me to this to your webinar. So I'm going to be talking about H1 constraints coming from the H1 intensity maps taken with the Green Bank telescopes, and particularly I'm going to be talking about the cross correlation with the eBOSS galaxy samples. I've got a little sort of schematic video what H1 intensity mapping is, in case someone doesn't know about it. So we are aiming to observe the large scale structure in the universe in order to do cosmology with it. And we do that by using the H1 emission that is present and coming from all the galaxies that compose the cosmic web. And you can see here just this little video highlighting how this all works. So everything emits H1 at the 21 centimeter line that then travels towards us, get redshifted on the way, and we can then observe it. And this is actually the Parkes telescope in Australia, because I made this graphic during my time when I was at the University of Melbourne. And so with a single dish, then we can see like a very low resolution map of the large scale structure, which is still good enough to do cosmology with it. And every frequency channel basically gives us a different map at a different redshift. So we can really efficiently observe a really big volume of the universe. That's the basic idea. And then do measure cosmology with these maps. So then what we usually do is when we've observed these maps with this low spatial resolution and usually quite high frequency resolution, we look at the 2-point correlation function, or the Fourier equivalent, which is the power spectrum. And again, this is a little graphic how this would look like, where the bold blue line is just a blank fiducial cosmology. And then I've marked a few variations to it. For example, if we have increased dark matter or an evolving dark energy model in these green lines. But then also the power spectrum depends on the H1 density, the cosmic overall H1 density, omega H1, the overall amplitude. So you can see there, if that is increased, the overall amplitude increases as well. But then also there can be also a scale dependence coming from the H1 bias. So how does the H1 gas actually trace the underlying dark matter structure? So, and then with these power spectrum, we can measure, for example, the BAO wiggles, as you can see here, and use that as a standard ruler to measure the expansion rate. But also there's other cosmology tests that we can do with it. Right, to quickly sum up why you probably haven't seen any cosmology results from H1 intensity mapping is that it's really hard. H1, as you all know, is a very weak signal, even though we're looking at the integrated H1 signal for many, many objects altogether. We still have the receiver noise that is higher than the signal for most instruments. It's definitely true for the GBT. Any sort of instrumental errors can go quite sensitively in those maps and mimic any cosmology or structure, particularly any sort of calibration uncertainties, side lobes, chromatic effects of the beam, pointing errors, and polarization leakage, which is actually one of the main systematics in their data I'll be talking about. RFI contamination is also a problem, as you're probably also all well aware of. But then really probably the arguably biggest issue that we have with H1 intensity mapping is that we have a really big foreground in between us and the H1 maps, which is coming from the synchrotron emission of our own galaxy, but also from extragalactic point sources. So we need to either avoid these foregrounds, or we need to have really good removal strategies in place that we understand what they do to the signal. So the GBT has first published the first H1 intensity maps in this work led by Eric Switzer and Kiyo Masuri in 2013. There were these two accompanying papers where they had observed two fields, the 1-hour field, which they called the wide field, and the 15-hour deep field, and it was a total of 40 square degrees. And the redshift range that's resulted from this observation was 0.6 to 1 redshift. So that's quite high when we think about cosmology surveys, which is really fantastic because it's observing an epoch of our universe that we don't know much about. And with that data, they didn't detect the H1 power spectrum directly. They only had an upper limit on it. And this is the plot that you can see here on the right-hand side. So this is the H1 auto power spectrum. And here these data points are the limits on it. However, they had a detection in the cross correlation of the H1 intensity maps with the Wiggles galaxy survey and resulting omega H1 BH1. So that's omega H1 is the energy density of H1 and BH1 is the bias constraints. So you can see here in the plot the upper limit, and in the red line, for example, that's the signal that we expect from the H1. So we are 1 to 2 orders of magnitude still too high, or we're too high there. However, you will see that hasn't changed that much. So when then I got involved with GBT data was basically when we suggested to do a different foreground removal method, which is called fast ICA, which works slightly different than the one they've used before, which is basically a version of PCA, principal component analysis. So we built our own pipeline starting from the maps. So we're dealing with the same maps, but then we do different strategies for the foregrounds and also the power spectrum estimator. And we got basically matching results, as you can see here. So the shaded regions are the previous results that Kyo was in the Masu et al. Paper, and then these points are the one that we produced with our alternative pipeline, which makes us quite confident that basically both pipelines are dealing with the foregrounds in a reasonable way. So now in the project I want to talk about, we basically took this further. We had some newer GBT data, some extended data, which was based on this work though before that, which is why I wanted to present it. And we got an agreement with the SDSS, the Sloan Digital Sky Survey, that we get access to the eBOSS galaxy samples that are in an overlapping field, and we cross-correlate them. And there were a lot of people involved in this project, and particularly it was co-led with Allergies Kurze, so I really wanted to point that out. And you can find it on the archive under this number if you'd like to have a closer look. So in this work, we looked at the GBT observations of the 1 hour field only. So the 1 hour field was extended to observations with 100 square degrees, but also in more depth. So the depth of that field is the same as the previous 15-hour deep field. So you can see here the 1 hour field, how it's overlapping with the eBOSS in the purple region. Similarly as before, we have 4 independent sets of maps from independent time stream data. So they have independent noise properties. All the maps are convolved to the same resolution with a beam of about ½ a degree. So that's a quite large scale. So that's more than 10 megaparsec, depending on which redshift you're looking. And again, we're using foreground subtraction with a fast ICA. This is just an example of how our data looks like. So in the upper left, you can see just the maps, again, as we got them. So I haven't touched the map making process. This is the same as was done before in the papers. You can see the foregrounds in them. On the upper right, you can see the inverse noise, basically by their scanning strategies, different depth in the data, particularly they're very shallow in the edges of the data. So they're very dominated by noise and systematics. And then in lower panels, you can see examples of a clean map where we basically get much better results if we discard the edges of the maps so that the foreground removal gets more into the structure in the middle. But however, this is still 1 to 2 orders of magnitude higher than we would expect the H1 signal here from a mock simulation. What we also did here for the first time with fast ICA is that we are looking at that we computed a transfer function with this data to correct for H1 signal loss that was introduced to the foreground removal. So we basically took the existing data and we injected mock H1 realizations and then applied the complete pipeline to it, and then looked how much of the mock injector data we have lost. And you can see here for relatively aggressive strategy where we remove 36 independent components, that's in the green line, you can remove up to 50% of the H1 signal on the very larger scales of the power spectrum. So we then use these transfer functions, as you can see them here, and apply them to the power spectrum to correct for the signal loss. And you can see also that it slightly depends on which different sections you look at, how the foreground removal performs, because the systematics are different in the different sections. So there's also different, this is very dependent on the systematics present in the data, basically, because when we looked at simulations and looked at the signal loss, it was basically nearly zero. All right, so this is then the resulting, again, auto power spectrum of the intensity maps, where again, we only have an upper limit. We are similarly as before, about 1 to 2 orders of magnitudes away from the expected H1 signal. However, it's nice to look at these just to see how it converges with foreground removal. So just to explain to you, in the upper crosses, you see the auto power spectrum between just two, I call them here seasons or sections, however you want to call them, basically, which is just the noise present. It's very, very dominant. However, if we correlate the power spectrum between 2 independent data sets, we get down to these lower levels here. And you can see here that for IC20, so independent components 20 and 36, we are starting converging to the same amplitude, which makes us quite confident that we are not over removing then signal, because this is corrected with the transfer function. Right, so then we are having our clean maps. They're ready to be cross-correlated with the galaxy samples. Now, for the first time, we have 3 independent galaxy samples, with the motivation being that we wanted to see if we can find actual different cross-correlations, because we expect these galaxy samples to be quite different in H1 content, and we know that that can leave a signature on the amplitude as well as the scale dependence on the cross-correlations. So we have the ELG from the eBOSS sample, which is the emission line galaxies, so quite blue galaxies, quite active star-forming galaxies. Then we have got the Allergy sample, the luminous red galaxies, which are usually very quiescent, big red objects. And as previously before, we also have the Wigglesdark energy survey, which is very, very highly star-forming and H1-rich galaxies. And you can see here the number densities as a function of redshift of all these 3 different samples. Okay, so now this is then the cross power spectrum between the H1 intensity maps and the 3 different samples, where they're marked in the same color. So the red is always the Allergy, the red galaxy sample, dark blue the ELG, and light blue is again the Wiggle sample. And you can see here that they are fairly consistent in amplitude and in shape. We have on the large scale, you can see we have these negative values. They just simply coming from the loss of the H1 signal, particularly in the line of sight from the foreground removal. So this is nothing to worry about. We do know where this comes from. And then here on the smaller scales of the power spectrum, we are completely dominated by the beam of the GBT observation. So we can't detect the signal then goes to 0 down because of this. So now we want to put also constraints on omega H1 from this cross power spectrum. So we need to have a model. So we're using this model here. So where we have the H1 power spectrum on the left-hand side, and on the right-hand side here is basically underlying dark matter power spectrum. And we have all these prefactors which are coming from the galaxy bias. They're coming from the H1 bias, as we discussed before. Then this averaged H1 temperature, which is just proportional to omega H1. And then also we have this factor R, the cross-correlation coefficient between those 2 samples, which is basically the correlation of how does H1 correlate with that particular type of galaxy that is selected in that sample. So we use that to just constrain the overall amplitude of omega H1, BH1 and the cross-correlation coefficient. We do not model any scale dependence, purely because we are limited by the data, and we have quite large error bars. So we can't, sadly, we can't attend that, even though that would be very interesting. And we also have a quite simplistic model for redshift space distortions. This is then how an example, so this is for GBT across the Wiggles data, looks like. So we have two in the black and gray, we have two different examples of how we remove the foreground, with 36 a quite sort of aggressive foreground removal and 20 which is a bit less aggressive but leaves just more noise in the data. And then we have fitted the model to it, and in order to take into account that we have a scale dependence of these factors that we can't model, we are fitting for different ranges of scale, where we believe that the green fit, so when we only fit for the larger scale, that is the most valid range for our model, because that's where we expect these quantities to be linear and not too scale dependent. And then on the lower plot, you can also see the significance of the data points. So we divided the data by the errors. Then the results on this, on the overall amplitude, you can see here for the different samples. So if we start on the lower left, so this is now the fit which I've just pointed out as a green line. So when we just fit the larger scales, you can see here that we get the highest amplitude. Also for different number of independent components, we get slightly different results, however, in agreement within the error bars. So we get the highest amplitude fit for the Wiggles galaxies, which is relatively expected because we expect them to be very, very age-rich, so they correlate more strongly with the GBT intensity maps, the H1 maps, and then it goes down with the ELG and then the LRG, because the LRGs are the most deficient in H1. We can also see that there's some decreasing values for increasing range of scales, which just simply says there is a scale dependence in these factors, which we're not taking into account. It is hard to pinpoint exactly where it's coming from, particularly with that sort of data that we're dealing with at the moment. And then we can go one step further. We can then make some assumptions from other works about the H1 bias and the cross-correlation coefficient. So we assume an H1 bias of 0.825 in agreement with the literature, and also cross-correlation factor for Wiggles R. And from that, we then derive the cross-correlation factor from our simulations that we have, and we get to a final constraints on omega H1, as you can see here, added in this plot. They all agree very nicely, so we are relatively confident that we make the right assumptions about BH1 and particularly RH1. Yeah, we're very, very happy to have these additional constraints for redshift 0.8. The summary is basically there's a lot of limitations in the data due to the systematics present that we don't know how to mitigate any further that we've already have. Foreground removal is definitely a very crucial step in the analysis. We constrain the amplitude of 3 basic independent cross correlations with the galaxy samples. We derive consistent results for omega H1. There's a lot of H1 intensity mapping experiments currently ongoing. One that I'm involved is with the SK Pathfinder Meerkat, so that's very exciting, and hopefully we can, push the field a bit further soon, and it can provide then constraints on cosmology as well as H1 astrophysics. Thank you.
Thank you, Laura. Okay, people can put their questions into the Q&A section. There was a question that came in during your talk. It was asking, I don't know if you can see it, it's under the chat. It was asking what you meant by mock here when you're talking about your simulations. I don't know if you want to
Okay, sorry, I stopped sharing, which was not my intention. I can get that up again. Apologies about that. I think I know what this refers to. I think that might have been the transfer function slide.
And then we have 2 people that have raised
their... No, it stopped sharing again. Okay.
That's okay. You can bring it back if somebody asks for a slide. Or unless you want to explain it based on your slides.
It might be easier. I know now what I did wrong. At least I learned from my mistake. There we go. So if I'm correct, that refers to this one here. So what mock realization in this means is that we have mocks of the H1 signal. So we are injecting it into the data as it is. And in this case, we're using, we create log normal fields, populate them with dark matter halo, and then use a simple H1 to dark matter halo relation to populate these dark matter halos with H1. And so we have 100 independent realizations of these fields, of these H1 realizations. And we all inject them independently into the data and apply the pipeline to it to derive these transfer functions.
Okay. We have a couple questions coming in. I'm wondering if we should just unmute them and let them ask it. Well, there's a question. I don't know if you can see the Q&A off to the side. You have to.
Yes, I can see it now.
Okay. You have did you want me to read them out? You just want to read them and take them?
I think, oh, really, so there was a question about ERGs, and I'm not quite sure if that's the ELG or the what this refers to.
Maybe we can, Paul, can you, there's a couple of hands up. Can you permit me, thank you for letting.
Sorry, yeah, I was referring to the extremely red galaxies that, yeah, the ELGs. Not the emission line galaxies, the very red galaxies.
Oh, the allergies, yes, of course.
Allergies. Yeah. Sorry, my bad. I mean, you know, you just wouldn't expect that those galaxies have any detectable H1 at all. But you know that they are in very unusually dense environments with lots of companions, lots of little galaxies that could have H1. Is it possible that that's what you're picking up in your 4 sigma correlation, their companions?
Yeah, it's a very interesting question. I mean, so when we used also some semi-analytic models and created light cones with magnitudes from it, and at the same, we tried to, you know, mimic the selection of the LRG sample. We actually found that they weren't that deficient because we are selecting, they're so big, so massive objects, there is actually some H1 left in them. So we didn't find that the cross-correlation coefficient was actually that low. I've also heard someone else in the eBOSS community commenting on that they are not that deficient in the way they are in the eBOSS sample. However, I think it was also likely what you've just mentioned on, because of the environment they're in, that just correlates with it. Yeah.
Yeah, we had another person chime in there saying, since they're seeing mostly clustered neighbors associated with them, not the ERGs themselves.
Yeah, it's a very interesting. It's a very interesting topic, how these correlate and how it comes from. Yeah.
I think we hit the questions in the Q&A. We have another user with their hand up. Okay, thank you, Paul.
Hello. Hello.
Hello.
Ask your question.
Hello. Can you hear me?
Yes, we can hear you. Go ahead, please.
All right, thank you very much. I just, you know, I couldn't somehow type a question in the chat. I just would like to this question quickly. I'm just curious. It's a very nice result, and especially cross-pulse spectrum. I do see that the in general behavior of the pulse spectrum doesn't much depends on the different types of galaxies, but I also noticed that there is the slight little bump around, you know, quarter, you know, inverse megaparsec. Do you consider that is actually an excess, or so it's just something completely ignorable?
So it's very interesting that the amplitude of the 3 samples is very similar. But obviously then we have the different constraints because, well, the amplitude of omega H1, because the galaxy bias for these different samples is actually very different, which goes into that. So now let me think about which feature you're referring to?
Around it's a 0.25, cubic inverse megaparsec at that round. I mean, I know the data is still noisy, but if I just use my eye and to draw the line by following those trends, I kind of see there's a little excess around that scale. I mean, I'm just curious how significant it is, or is it not something we should as a significant?
I mean, you can see significance here. We have in general relatively low significance. So we would not make any statements about the shape of the power spectrum with the current, knowing how systematics contaminated they are.
Okay, thank you.
We had another question come in. Did you want
yes,
answer?
okay, yes.
Did you see that?
The MeerKAT survey, yes. So currently, MeerKAT is observing, so the survey is called MeerKAT, and there's a paper led by Mario Santos on the archive on the MeerKAT proposal. The final survey is a 4,000 square degrees with 4,000 hours, quite easy to remember. At the moment, we're doing observations in the L-band. So we are looking at a redshift band because there's also quite a lot of RFI. So we're looking around 0.2 to 0.4 redshift. So we're looking at lower redshifts at the moment. There's a lot of work going into the calibration pipeline because we're using MeerKAT as a single dish array rather than interferometer. So there's a lot of work that goes right now into the infrastructure. However, there is discussions if we are soon using the UHF receiver to go to higher redshift and do some pilot data. So it's all very, very moving at the moment.
Okay. Another question came in through the chat, and I'll just read it off. What is the dominant uncertainty in your Omega H1 measurement?
The dominant uncertainty?
Yeah.
Well, we have obviously calibration errors as well, which I don't think I've mentioned before. There are systematics in it, which we cannot. They are coming from you. It is suspected it is polarization leakage, and because of that, we have excess power that we can't remove.
And another question, any data possible from CHIME?
Well, I don't know that. I'm not in CHIME. I mean, I know people are working on it. I have not managed to get a glimpse on it. So I am as curious as you.
And I had just had a general question in terms of the trade-offs, in terms of going lots of small areas and going really deep versus going shallow and very wide. I don't have a sense on how that plays out and gets you what you want to get in terms of luminosity function or your constraints on a Mega H1. Do you have, I know this is pretty general, but do you have anything you would like to say on that?
Yeah, it's a trade-off. I mean, obviously, since we are most of the surveys are designed to detect the BAO, for example. That's what MeerKAT and MeerKAT wants to do. So it usually go wider and go just deep enough that your signal is above the expected noise. But having said that, if you wanted to do it as an interferometric experiment, you would go deeper. So you just get more and more signal to noise because you don't want the large scale information in that case.
Okay. Excellent. Let's see, did we get?
There's another question.
Yeah, there is. Go ahead.
So questions, how are you sure that independent component that you extract belongs to the foreground? Yeah, that's a very good question. We are actually, we know that the ICA also, so the way the fast ICA works is that a fast ICA doesn't decomposes signal depending on their non-Gaussianity. so basically in this case, we assume that the H1 signal itself is a very Gaussian-like signal. So it's actually not a component of the analysis, it's just the residuals, it's the errors that are left over once we have modeled all the components with fast ICA. So obviously we have seen that still something you can still lose signal through it. We do also know that it's not just foregrounds. The fast ICA models a lot of the systematics, RFI, anything that is non-Gaussian, it will model in it, which is a good thing, and which is why we are actually having to use 36 independent components, because with all simulations where you don't have any systematics or instrumental, like significant instrumental effects, you only need something like 4 to 6 independent components. So this is really a testament that you have a lot of other signal in there, and the ICs are modeling it, which is actually really good.
Okay, great. Anybody else have additional questions for Laura? Okay. I do not see, let me check looks like you answered it. Oh, I'm trying to get my cursor to move. Okay. Well, thank you very much, Laura, for an excellent presentation. Quite interesting data. And thank you for everybody for attending. And I believe we'll have another one of the GBT webinars in 2 weeks. So thanks again, Laura.
Thank you very much.
Okay. Bye now.
Bye.
Everybody.